Değerli katılımcılar, değerli dostlar, sosyal medya platformları üzerinden bizi izleyen güzel insanlar, herkese merhabalar. TÜBİTAK Temel Bilimler Araştırma Enstitüsü, temel bilimin çeşitli dallarında ve disiplinler arası alanlarda düzenlediği uluslararası seminer serileriyle en üst düzey ve yenilikçi bilgileri ülkemizin bilim ve eğitim camiasına aktarmaya devam etmektedir. Bu akşam yine bu vesileyle Astronomi ve uzay bilimleri seminer serimiz kapsamında harika bir seminer gerçekleştirmek üzere bir araya gelmiş bulunmaktayız. Bu sefer İngiltere'nin King's College London Üniversitesi'nden son derece değerli bir bilim insanı Profesör John Ellis ile efektif alan teorisi ile standart modelin ötesine bakmak konusunu konuşacağız. Ben de bu vesileyle hepinizi her zaman olduğu gibi saygı ve sevgiyle selamlıyorum. Seminerimiz İngilizce olarak gerçekleştirilecektir. Bu nedenle İngilizce devam edeceğim. Dear Professor John Ellis, dear participants, dear colleagues and friends, a very warm hello everyone and welcome. Welcome to the inspiring online seminar series of TÜBİTAK Research Institute for Fundamental Sciences. We organize these seminars for national and international audiences, relying on unifying feature of science for humanity and with the participation of distinguished scientists and great speakers of the world. We also organize these seminars to mitigate the negative impact of COVID-19 situation in the world on scientific thought and its creation. It is now my pleasure to inform you that this evening we have another wonderful episode of our Astronomy and Space Sciences seminar series, and I have a distinct pleasure and honor to introduce you our very special speaker, a wonderful person, distinguished physicist and world-class expert in the field, Professor John Ellis from King's College of London, United Kingdom. Professor John Ellis has kindly agreed to join us for this seminar, and he's going to give a great talk, looking beyond the standard model with effective field theory. At the end of the talk, we will have Q&A session, where questions can be asked by sending a message through chat button of the Zoom platform, or just by raising hand. John Ellis currently holds a Clerk Maxwell Professorship of Theoretical Physics at King's College in London. After his PhD in 1971 from Cambridge University, he worked at SLAC, National Accelerator Laboratory operated by Stanford University, Caltech, and CERN, Geneva, where he was theory division leader for 6 years. His research interests focus on the phenomenological aspects of elementary particle physics and its connections with astrophysics, cosmology, and quantum gravity. Much of his work relates directly to interpreting results of searches for new particles. Professor John Ellis was one of the first to study how the Higgs boson could be produced and discovered. He is currently very active in efforts to understand the Higgs particle discovered recently at CERN, as well as its implications for possible new physics, such as dark matter and supersymmetry. Professor John Ellis also studies possible future particle accelerators, such as the compact linear collider and future circular colliders. He is known for his relentless efforts to promote global collaboration in particle physics. Professor John Ellis was awarded the Maxwell Medal in 1982 and the Paul Dirac Prize 2005 by the Institute of Physics. He was elected Fellow of the Royal Society of London in 1985 and of the Institute of Physics in 1991, and is a honorary fellow of King's College, Cambridge, and of King's College, London. With this, I want to thank sincerely once again Professor John Ellis for joining us this evening and invite him to the stage to begin his talk. John?
Okay, well, thank you very much, Alikram, for that very nice introduction. So let me just share my screen.
Okay, it's perfect.
Okay, let me just go to full screen. Okay, well, thank you again for this kind invitation to talk to you and other Turkish friends. I'm very sorry that I cannot be with you in person. I have many fond memories of visits to Turkey, and I look forward to meeting with you in person in the near future.
Sure.
So today, as was already mentioned, I'm going to be talking about ways to look beyond the standard model with effective field theory. And as a sort of motivation for this, I choose this quotation from the Chinese strategist Sun Tzu. So the direct method of looking for new particles may be used, but indirect methods will be needed in order to secure victory. The direct and the indirect lead on to each other in turn. It's like moving in a circle. So I'm not sure whether he had in mind a circular collider, but anyway, that's going to be perhaps my interpretation. Who can exhaust the possibilities of the combination of the direct and the indirect approach? So that's what I want to talk about in this presentation. Well, let's start off by reminding ourselves of where we are with elementary particles at the moment. So on this slide here, I've summarized the standard model. So in the top half of the slide, you've got the particles of matter and their SU3 cross SU2 cross U1 quantum numbers. So we have doublets of left-handed leptons and quarks. The right-handed leptons and quarks are singlets. As I said, we've got SU3 cross SU2 cross U1 interactions described by gauge theories. And if you look in the bottom half of the slide, you see a Lagrangian. The first line of that describes those fundamental gauge interactions. The second line of that Lagrangian describes how those interactions work upon the fundamental particles of matter, the quarks and the leptons listed in the top half of the slide. Now, before the LHC started up, those top two lines of the standard model Lagrangian had been tested with an accuracy better than the 0.1% level in many cases. Now, the two bottom lines of the Lagrangian are the terms which involve the Higgs boson. So you see here a field phi, which couples to fundamental fermions through Yukawa interactions on the third line. And the bottom line, you see a kinetic term for the Higgs field and the Higgs potential. And LHC experiments now are just testing those terms in the Lagrangian involving the Higgs boson. So on the slide here, I've taken a summary of measurements by the CMS experiment at CERN. On the right, you see measurements on production of the Higgs boson at the LHC. And to the left, you see the results from many other measurements of processes involving standard model particles. And in general, what you see is that the measurements, which are shown by the colored symbols, are in good agreement with the theoretical calculations represented by the gray lines. And that's in particular the case for the Higgs boson production mechanisms, which you see over here on the right-hand side. Now, the Higgs boson was, of course, discovered on July the 4th, 2012, almost 10 years ago. And in fact, when it was discovered, the experiments were looking for the Higgs boson, and they found something which corresponded to the signal that they expected. But of course, it could have been an imposter, and it was very important, following the discovery of this new particle, to check whether it really was the Higgs boson predicted in the standard model. So I compare this to trying to complete a jigsaw puzzle. You know how it is. There's a piece that's missing, and eventually you find a piece of bent cardboard sitting at the back of the sofa. The picture's been rubbed off. Does this have the right size and the right shape to complete the jigsaw puzzle? So this is something that the LHC experiments worked on in the years following the discovery of this new particle. And here is a compilation of recent measurements, again by the CMS experiment. So what they're checking here is whether the couplings of the Higgs boson, represented on the vertical axis, are proportional to the masses of other particles shown on the horizontal axis. Because the Higgs boson gives other particles their masses, the couplings should be strictly proportional to their mass. And that prediction is shown here as that dashed line. And what you can see is that the measurements agree with that prediction very well, all the way from the heaviest known particle, the top quark, through the WZ, bottom, and tau, down to the muon. So over many orders of magnitude, the prediction of the standard model for the couplings of the Higgs boson are consistent with the experiment. But some people might say, well, you've just found the last particle in the standard model. There's nothing more to do. Let's go do astrophysics. But I would argue the opposite. And I would take as a quotation these two lines from a poem by the poet T.S. Eliot. So he wrote a poem called Little Gidding, and this is actually an aerial view of Little Gidding, which is a village in England. And in his poem, he wrote, "To make an end is to make a beginning. The end is where we start from." So my interpretation of that is that by completing the standard model, we are now in a position, a firm basis, to start looking for physics beyond the standard model, a beginning of beyond the standard model physics. So the obvious place to start is by thinking about the Higgs boson. And on this slide, I want to emphasize that pretty much everything about the Higgs boson is puzzling. So outlined in red here at the top of the slide, we have the terms in the standard model Lagrangian which involve the Higgs field H. So first, we have the couplings of the Higgs boson to fundamental fermions, the so-called Yukawa couplings Y. Now, I already commented that the masses of fundamental particles vary over many orders of magnitude, and the couplings of the Higgs boson correspondingly vary over many orders of magnitude. Where do these couplings come from? Why are these masses so different? Why, in the weak interactions, do the different quarks mix in the way they do? And this is all linked together in what we call the problem of flavor. And the second term in the standard model Lagrangian is the mass term for the Higgs boson, mu. So there's a couple of questions here. One is the sign of that mu squared, mass squared term. And the other one is its magnitude. So the only candidate we have for a fundamental mass scale in physics is the Planck mass, which is 10 to the 19 GeV. But the Higgs, we know, weighs about 125 GeV. So what explains this hierarchy of masses between the Higgs scale and the gravity scale? And how is that enormous ratio made a natural feature of the theory? Then we come to the third term in the Standard Model Lagrangian, which is the quartic-Higgs self-coupling. Now that has to be positive in order to give you a stable minimum of the effective potential. But calculations in the Standard Model indicate that when you go to large values of the Higgs field, the effective value of lambda changes sign, generating an instability. The electroweak vacuum, empty space, seems to be no longer stable. And then, of course, we have to allow for the possibility that there's a constant term in the Standard Model Lagrangian, so-called cosmological constant or dark energy. And in fact, we know from observations of cosmology that that dark energy is non-zero. It's not so much that a puzzle that it exists. What is a puzzle is why it is so incredibly small. Again, it raises problems of naturalness and hierarchy. Now, in addition to these known or expected terms in the Standard Model Lagrangian, I've added here some dots, and those dots represent possible higher dimensional interactions of higher order in the Standard Model fields that might be generated indirectly by the exchanges of massive particles. And that's what we're going to be discussing in the rest of this talk. So these possible higher order effective field theory interactions have had a long and glorious history. So if you think back to the 1930s, we had an embryonic theory of quantum electrodynamics with electrons coupled to photons through a dimension 4 interaction. But we also had Fermi's 4-fermion effective field theory of the weak interaction. So this involved 4 fermions interacting at a point. That is an interaction which has dimension 6. Of course, there was a question, what is the Lorentz form of that interaction? Is it scalars, pseudoscalars, vector, axial, maybe even tensor? What you might have thought was that this dimension 6 interaction was generated by the exchange of massive particles. Now, in the 1950s, it was established that this interaction had the form of current-current, vector currents, axial currents, which could be mediated by the exchange of massive vector bosons. And that drove the theoretical attempts to make a theory of massive gauge bosons, which resulted in gauge theory, spontaneous symmetry breaking, and the Higgs mechanism. Now, in parallel, in the strong interactions, Yukawa in the 1930s postulated his meson theory of the strong nucleon force. The lowest mass meson is, of course, the pion. And when people looked at the effective interactions of those pions, they discovered they had a very particular property called chiral symmetry, which meant that they had these characteristic derivative interactions. And that was actually a very important clue that the underlying theory should be based upon vector gluons. And that's what led us to formulation of QCD. So effective field theories played a very important role in finding the form of the weak interactions and also finding the form of the strong interactions. So maybe effective field theories now will lead us to whatever lies beyond the standard model. So what we're doing now is we are looking at a standard model effective field theory in which we assume that the terms of the standard model Lagrangian are correct. The quantum numbers of the particles are as predicted, but there are additional interactions due to the exchanges, presumably of heavier particles, which have higher dimensions. So we write down all those possible extra interactions, and then we analyze the data on the Higgs boson, electroweak precision data, production of the top quark in terms of this standard model effective field theory. And this, as I will discuss, is the most efficient way to extract the largest amount of information from LHC and other experiments, and at least almost model-independent way to look for possible physics beyond the standard model. Okay, so many people have been working on this program, and in most of this talk, I'm going to be discussing an analysis that I did a while back together with Maeve Madigan, Ken Mimasu, Veronica Sands, and Tivong Yu, where we included all the leading dimension 6 operators, a priori, there's 2,499 of them. And so because they have dimension 6, they're scaled inversely by some large mass scale lambda squared with numerical coefficients, which I've denoted here by Ci. Now, in order to simplify things, we and others often assume some sort of flavor symmetry for the interactions involving fermions. Either they're completely flavor symmetric, SU3 to the 5th, or the symmetry is broken for the top quark couplings, in which case we have an SU2 plus SU3 cubed symmetry. So we worked to linear order in the contributions to amplitudes of these operator coefficients. One can work to higher order, and I'll mention that briefly later on. So here is a table showing the relevant dimension 6 operators. So some of these involve just bosons, like these ones up here. Some of them involve pairs of fermions, like these over here. Some of them involve 4 fermions, like these down here, for example. Now, the various different entries here are color-coded according to how they are constrained by different types of measurements. So Higgs measurements, electroweak precision measurements, top quark measurements, and so on. The gray boxes indicate interactions where there might be breaking of the SU3 to the 5th symmetry that I'll come back to. And those are particularly important when you're thinking about observables involving the top quark. Now, additionally, I've highlighted here in green operators that could contribute to flavor anomalies, like those perhaps observed in B decays. In orange, I've listed the operators that contribute to anomalous magnetic moments, like G-2, and in purple, I've illustrated the operators that contribute to baryon decay. So I'm not going to be discussing all those in this talk. I'm going to be concentrating in the ones that are shaded beige, blue, and I guess that's it. So if you postulate SU3 to the 5th symmetry, there's 20 such operators. So some of them contribute in particular to electroweak precision observables, some of them to bosonic observables, some of them to modify the Higgs Yukawa couplings. If you relax to this SU2 cross SU3, SU2 squared cross SU3 cubed symmetry, breaking the flavor symmetry of the top quark couplings, then you get a total of 34 operators. Now, these different operators can contribute to many different observables. And each of the observables can get contributions from several different operators. So, for example, these operators here contribute to the production of pairs of W bosons. But they also contribute to top electroweak couplings. And they contribute to precision electroweak observables. And they contribute to Higgs observables. So this emphasizes that if you want to constrain the coefficients of those operators, then you need to consider all these possible sectors. And so that's what we did in our analysis. We made the first global fit to precision electroweak data, dye boson production, top production, and Higgs production. And we used those data to search for physics beyond the standard model, both at the tree level and at the loop level, as I'll discuss later on. Now, I should mention that these dimension 6 operators make larger contributions to cross-sections at higher energies, higher invariant masses, and larger transverse momenta. So what we do is we break the data up into different kinematic regions. And for example, the higher PT regions, highlighted here in red, give you greater sensitivity to dimension 6 operators. Of course, at high PT, you get lower statistics. So, you gain some, you lose some. But it's important to include this kinematic information as well as total cross-section measurements. So in our analysis, we included a total of 328 experimental measurements. So electroweak precision observables from LEP and the tevatron, dye boson production, Higgs production runs 1 and run 2 of the LHC, top production run 1 and run 2. And as I mentioned, we included a lot of kinematic information as well as total cross-sections. So here on the right-hand side of this slide, I illustrate for you some of the results from a fit where we assume flavor universal SU3 to the 5th symmetry. So in the top half here, we just switched on one operator at a time. So 0 here, that corresponds to the standard model with no modifications. And you see that that is consistent with all these measurements. There is no evidence for physics beyond the standard model from this dimension 6 analysis. What you can derive is upper limits on the coefficients, which can be translated as lower limits on the possible scale lambda of these additional operators. And you can see that these are measured in TeV, sometimes tens of TeV, sometimes 1 TeV, sometimes, in particular in the top sector, a fraction of a TeV. Now, in the second half of the slide here, we did a fit where we switched on all the operators simultaneously, and then we evaluated the constraints on individual operators, marginalizing over the possible values of the coefficients of the other operators. So when you do that, you get a weaker constraint. You still find consistency with the standard model, but in this case, the low limits on the operator coefficients lambda are typically somewhat smaller. Now, I'd like to emphasize again that it's really essential to do a global analysis, and it's also important to include all sorts of kinematic dependencies. So in this slide here, you see that, for example, these operators here get important constraints from this measurement, this measurement, this measurement, this measurement, and that measurement. And conversely, you see that this measurement is important for constraining this operator, this operator, this operator, and this operator. So you really have to include everything globally in your analysis. So the previous results were assuming flavor universality. But maybe that flavor universality is broken for couplings involving the top quark. So you study that with this reduced SU2 squared cross SU3 cubed symmetry. Again, in the top half of the picture, you see the constraints switching on one operator at a time, and in the bottom half, the constraints that you get where you switch on all the operators and then you focus on one operator, marginalizing over the coefficients of the other operators. So again, you find that many of the operators are constrained at the 1 to 10 TeV level. But here you notice in particular that the constraints in the top sector are weaker. Also, if you look very closely here, you can see that there's one example of an operator that seems to want to have a non-zero coefficient. I'll come back to that in a moment. I don't think that evidence is significant, but I will at least spend some time discussing it. Now, the fact that many different observables contribute to each of a number of different operators means that you tend to get correlations between the constraints on the coefficients of different operators. And that's illustrated here. So for example, you get quite strong correlations between the coefficients in the electroweak and bosonic sector. And you also get some quite important constraints in the top sector. You also get some correlations in the off-diagonal sector. So there's correlations appearing also between the coefficients of top operators and purely bosonic operators. And this has to be borne in mind. So for example, I think it's a shortcoming if you do a fit where, say, you just fix all the electroweak observables to their standard model values and try to analyze the rest of the observables. I think you're losing important information when you do that. So let me give you one example of the interplay between the various different sectors of data. So here I consider a handful of operator coefficients, CTH, CTG, and CG, and on the horizontal axis, HG, TH, TG. So if we put in the Higgs data without the top quark, then we get this beige preferred region. Not a very strong constraint. If we include TT bar H production, we get a much tighter constraint, shown here in green. But when we include the top data, the constraint gets much stronger still. And if you do a global analysis, that's the result that's shown here by this darker shaded oval. So all these different data sets cooperate to give you the tight constraint. So now, let's just look at the bottom row. So what you see is that this global ellipse seems to miss the value 0 for CG. It seems to be wanting that coefficient CG to be non-zero. So is that effect real? And we don't think so. So this effect is driven in particular by the top data, and especially by the invariant mass distribution of TT bar. And so the data are shown here as the black points, normalized relative to the standard model. And you see that the agreement between the two is not so great. Here's the best fit value shown as the little yellow star. And that best fit seems to want CG non-zero. But you see here that the dominant deviation is actually at relatively low energies, low invariant masses, which is not where you'd expect dimension 6 operators to contribute. You'd expect dimension 6 operators to contribute over here. And in fact, other people have done analyses of jet data which also favor a small value of CG. So I think that this evidence for a possible non-zero coefficient of CG should not be taken seriously. And I wonder whether there's some effect at low invariant masses in these data that hasn't been taken fully into account. So, as I already mentioned, the limits on these operator coefficients are correlated, and you can diagonalize the correlation matrix and see which combinations are most strongly constrained, and if so, by which data. So you see here the most strongly constrained combination, which is indeed constrained by a combination of electroweak precision observables, Higgs production, and kinematic information. And over here you see the operators which are most weakly constrained, and these are the ones that are only sensitive to top data. So, generally speaking, the strongest constraints come from electroweak data, the weakest from top data. Okay, so now I want to start discussing explicitly constraints on physics beyond the standard model. So the simplest possible model beyond the standard model is to identify a single additional field. So you can make a catalog of all the possible single field extensions of the standard model. So some of them have spin 0, some of them have spin 1, and some of them have spin 1/2. Let me focus on spin 0 and vector. So there are just a few examples of such possible extensions of the standard model. Now, if you add in just one of those fields, then it will contribute to a limited number of operator coefficients. So for example, this one here, which is a singlet scalar model, contributes basically to just one operator. On the other hand, there are other examples. For example, this vector particle here would contribute to several different operator coefficients. So we analyzed each of these single field beyond the standard model scenarios, and we analyzed them in two ways. One is assuming that their coupling to standard model particles was unity, in which case we got constraints expressible in terms of TeV. And another one where we assume the mass is 1 TeV and find out what is the constraint on the coupling. I should say that in no instance did we find any significant evidence that any of these fields was present. And typically, for couplings of order 1, we got constraints on the scalars which are of order TeV, and constraints on vectors of the order of 1.5 TeV. Fermions, no, some of them could be a bit lighter. Okay, so again, no evidence for physics beyond the standard model, and limits which are, roughly speaking, the TeV scale. So those were limits at the tree level, just looking at individual couplings of the beyond the standard model particles to standard model particles. Now, the extensions of the standard model where the SMEFT contributions are generated by loop diagrams. And one example of that is supersymmetry. So here are the contributions of the stop squawk to a set of operator coefficients, which come from loop diagrams. So you've got these factors 1/4π². So we looked at those operator coefficients globally, and we used them to derive the constraint on the stop squawk mass as a function of the way in which the two stop squawks, as there's two different types of stop squawk, so the constraint is on the lighter stop squawk as a function of how it mixes with the heavier stop squawk. And as you can see, we get limits which are typically a few hundred GeV, depending on how much mixing you have. So it's interesting to compare that, what I would regard as being almost model independent limits, with direct searches. Now, the direct searches are very complicated because the spectrum of supersymmetry enters in, there's many parameters, and some of the corners of parameter space are really quite complicated to analyze. So, for example, this is from an analysis by Atlas, and there was a very delicate region down here, which they worked very hard to exclude by a combination of different searches. Now, what the indirect method does is it basically puts a lower limit, which is largely independent of the masses of all other supersymmetric particles. And as you can see, it's of interesting order of magnitude. And this, I think, strengthens the conclusion of the LHC that the stop squawk cannot be very light. So I've given a couple of examples of extensions of the standard model which contribute to several operator coefficients. So the second one was the stop squawk, and previously there were examples, for example, vector boson extensions of the standard model. So that motivated us to look at all possible 2-operator, 3-operator, 4-operator, and 5-operator extensions of the standard model, but without any particular beyond the standard model scenario in mind, but just to look to see whether the data were pushing for any of those combinations of operator coefficients to be non-zero. And the answer, I think, is no. Certainly, the operators which don't include top quarks, they don't seem to be wanting to pull you away from the standard model. Operators including the top quark, well, yeah, maybe some of them, but as I pointed out, I think there's issues in the top quark data. Overall, we didn't feel that any of the pulls away from the standard model were significant, and we don't think that this analysis provided any hint for physics beyond the standard model. I should mention, by the way, that there's something like 300,000 different combinations of operators in these plots here. No evidence for physics beyond the standard model. So several months after our paper, there was another paper by the Smefit collaboration where they included also second order terms in the dimension 6 operator coefficient. So these are of order 1 over lambda to the 4th. So in general, they got somewhat tighter constraints. But I worry a little bit that if you're going to order 1 over lambda to the 4th, you should also worry about dimension 8 operators that in principle also contribute at order 1 over lambda to the 4th. And Smefit did not include dimension 8 operators. It's in general very, very complicated. There's many, many, many dimension 8 operators. However, one of the things that interests me is that there are some windows of opportunity for looking directly at dimension 8 operators. And these are offered by light scattering, by glue goes to gamma gamma or Z gamma, and by looking at triple neutral gauge boson couplings. And in the last few minutes, I just want to mention some analyses that I've been involved with of dimension 8 operators. So my interest in this was triggered actually by a paper by Atlas a few years ago that observed for the first time light by light scattering in heavy ion collisions at the LHC. Now you expect light-by-light scattering in the standard model from fermion loops. And those were first calculated by Heisenberg and Euler in 1936. What we pointed out is that you can use these data not just to check Heisenberg and Euler, but also to constrain nonlinearities in electrodynamics, such as might be generated by Born-Infeld theory. So this is a slide showing some formulae from the paper by Heisenberg and Euler, written in this wonderful Gothic script. Now, what did Born and Infeld do? So Heisenberg and Euler had calculated what we would call standard model loop diagrams. What Born and Infeld did was they said, well, maybe there are nonlinear interactions in the gauge field strengths. And they proposed this based on what they called a Unitarian idea of a maximum possible electromagnetic field, in the same way there's a maximum velocity of light. So that was the idea. I think many people said, well, you know, it sounds a little bit cockeyed. But amazingly, in the 1980s, Fredkin and Saitlin showed that these sorts of nonlinearities arrived in string theory. And in the 1990s, Bachas showed that the degree of nonlinearity was related to the velocities of branes in brain world scenarios based on string theory. Amazingly, Born and Infeld were right. The value of that coefficient was related to the velocities of d-branes. So we were able, together with Nick Mavromatos and Tivon Yu, to use the Atlas data to set lower limits on the possible mass scale in Born-Infeld theory, which could be translated into constraints on brain models of string theory. Subsequently, the Atlas collaboration made a nice measurement of diphoton production at the LHC. And together with Charles Gre, we realized that that could be used to constrain dimension 8 4 boson interactions in a general way, 4 boson interactions involving a pair of gluons, which again might be generated in a Born-Infeld extension of the standard model. So these dimension 8 operators would make contributions to the cross-section that grew very rapidly with energy and which would have a completely different angular distribution from what you'd expect in the standard model. So we used the Atlas data to derive lower limits on the coefficients of these dimension 8 operators, which were of the order of a TeV or so, and future colliders could push those limits up to many TeV. So we think that not only light-by-light scattering, but also glue goes to diphoton production, provide a unique window on dimension 8 physics. Now, just recently, again with Xiaofeng Ge and with Kai Ma, we've extended this analysis to include glue goes to Z plus photon. So here the analysis is a bit more complicated because you've got 3 different decay modes of the Z to consider into charged lepton pairs, neutrino, antineutrino pairs, quark-antiquark pairs. So you can analyze each of those independently. You can also compare with the constraints that you get from gamma-gamma production. And here we actually updated our previous results to include the full 1,2 luminosity. So this is the final plot from our paper. So it's a bit complicated, and I won't go through all the details. So we derive constraints for each of 8 different operators coming from gamma gamma and the various different Z gamma final states and the combined result. And we considered constraints coming from current LHC data and future LHC data and possible future collider data. And so what you see is that the current limits go from a few TeV up to potentially in the future 20 TeV. So for example, just focus on the constraint on Born-Infeld theory. So at the moment, it's about 3 TeV, and eventually it should go up to above 20 TeV. So that brings me pretty much to the end of what I wanted to say. So remember what Sun Tzu said at the beginning of my talk. If you're looking for new physics beyond the standard model, look indirectly as well as directly. Look through the standard model effective field theory as well as direct searches for new particles. And I hope I've convinced you that the standard model effective field theory is an effective model-independent tool for probing indirectly possible physics beyond the standard model. And the great thing about it is it provides you with a framework that you can use to analyze jointly precision electroweak data, dye boson data, Higgs data, and top quark data from the LHC and elsewhere. So very roughly speaking, our analysis of the current data indicates that the scale of new physics is probably bigger than of order a TeV. In some cases, the constraints at the level of 10 TeV, some cases level of a few hundred GeV, but generally speaking, the LHC is already hinting that we need to look for new physics at the TeV scale and beyond. And as I illustrated with the example at the end, standard model effective field theory is also potentially useful for assessing sensitivities of proposed future accelerators. So I come to my final slide. So here we have the standard model represented by the Titanic, and it's sailing along happily, and it sees this tip of an iceberg of the standard model interactions with dimension 4. But beyond the standard model interactions written on the standard T-shirt, there are possible effective field theory interactions with dimensions bigger than 4. And these potentially are much bigger than, much more than the dimension 4 interactions, in the same way that the hidden part of an iceberg is much larger than the visible part. And it may well be that the standard model is going to be sunk in a collision with these higher order SMEFT interactions. Thank you.
So thank you so much for this very deep and intriguing talk. Now we can pass to questions. Please send us questions or ask. John, what is about G minus 2 factors? So recently was also many discussions about this, and you also talked about it. What is the final situation there?
So the situation, as you know, is that there's a discrepancy between the experimental measurement and the theoretical calculations based on low energy E plus E minus data, which is about 4 standard deviations. Now, you can describe that discrepancy in the framework of the Standard Model effective field theory. So here I've outlined the operators which contribute, in particular the two operators at the top here, where you've got a lepton and you've got a couple of bosons here on the right-hand side. Now, you can analyze the discrepancy using the Standard Model effective field theory, as I said, assuming, of course, that the mass of the new physics is above, I would say, above a few GeV. Okay? Because the dominant Standard Model contribution comes from physics below 1 GeV. Now, in general, people have not done that. They looked at specific extensions of the Standard Model, and many of those extensions postulate new physics in the hundreds of GeV range. So one example is supersymmetry. So supersymmetry could generate this anomaly in G-2 if you had, for example, a relatively light supersymmetric partner of a muon and a relatively light dark matter particle weighing a few hundred GeV. And so this sort of operator description would be a valid way of analyzing that particular model, although what people normally do is calculate Feynman diagrams. Now you might ask whether such a supersymmetric interpretation of G-2 is compatible with LHC data, because we keep on hearing, oh, well, LHC tells you that supersymmetric particles must weigh more than a TeV, blah, blah, blah. Well, that's true for strongly interacting supersymmetric particles. It's not so true for the Stokes quark, as I showed you earlier on in my talk. And it's not true for the supersymmetric partner of the muon. Supersymmetric partner of the muon could be as light as 100 GeV. That would still be allowed by the LHC. So for me, the origin of this discrepancy between experiment and the Standard Model calculation is still an open question, but it could be explained by supersymmetry within reach of the LHC.
Thank you. More question, please. So if no more questions, perhaps we can stop here, John. We can close session.
Okay.
So thank you once again so much for joining us for this seminar. And I very much hope that we will meet when this COVID situation finally gets resolved in the world.
Yeah,
so if you want to make final remarks, please make.
Okay, well, just to say thank you again for the invitation. And really, I think the world is beginning to open up. I was actually in Dubai a couple of weeks ago, and I survived perfectly well. I think I mentioned that I've now got COVID, although it's a very mild case of COVID. But I didn't get COVID in Dubai. I got COVID in London. So I don't know what's the COVID situation in Turkey nowadays, but I suspect it must be better than it is in London. So
now it's much better, of course.
Right. So I look forward to meeting you in person shortly and revisiting Turkey.
Sure. So take care of you.
Okay.
Let's wait